Hello everyone, welcome back for another video in the series. So let's now take a look at more hands-on example to get more hands-on training on adaptive linear neuron in Python. So first, I will give you the overview of how things relate to the ADALINE. So recall the ADALINE, that is what we covered briefly in the history of deep learning. That is a model by Woodrow and Hoff and developed around the 1960s. So actually, it was a physical device, but you can think of course, nowadays it can be implemented in software as well. And this is nicely differentiable neural model. So the perceptron model that we talked about before is not differentiable because of this threshold function. And this ADALINE, you can think of it as an advancement of this perceptron that is now also converging, even if the data is not linearly separable. So just for comparison, how the perceptron look like, recall in perceptron, we computed the net input first, and then we pass the net input through the threshold function, and then the threshold function produces our output. So the output is predicted class label, which can be either 0 or 1. And if the prediction matches the actual label for that given training example, then we don't do anything. But if it doesn't match, if it's different, then we do this error term that we computed. So we have the difference between the two, and we use that to update the weights, which then will change the decision boundary to make the prediction correct. So that is how the perceptron works. But a threshold function is not differentiable. So here we couldn't use calculus. So it was more like an empirical update rule. Now we can actually improve that by using calculus. So at the bottom here is ADALINE. And here you can think of this part here as maybe base model, and this is like linear regression. So again, we also compute the net input similar to the perceptron. Now we have as an activation function, we have this identity function which is not doing anything. So if it's not doing anything, if my activation function is just the identity function, why do I write it down in the first place? That's because in the coming videos, we will be talking about nonlinear activation functions. We will be talking about functions that are, for example, sigmoidal function, and also we will be covering other types of activation functions as well. And we will need them to develop multi-layer neural networks, because this will help our multi-layer network to produce nonlinear decision boundaries for solving complex problems. Because if we would be using linear activation functions, the multi-layer neural network, then the multi-layer network would be just a combination of linear functions, and the sum of linear functions is also just a linear function, so we wouldn't gain anything. And later on we will be talking about nonlinear activation functions, and here you can think of it as a placeholder. We will replace that later. I'm just including it here in the notation because it's a more general notation that would apply to also nonlinear activation functions. And now consider this linear regression base. In order to turn this linear regression model into an adaptive linear neuron into this ADALINE model, all we have to do is now adding a threshold function, because ADALINE is a classifier. So this is a classifier for classifying data points similar to the perceptron. However, note the difference here really between the perceptron and ADALINE is where we compute the error. So for the perceptron, we compute the error after the threshold function, and in the ADALINE, we compute the error before the threshold function. So here we wouldn't. So here we don't have the problem that things are not differentiable, because we compute the error before the threshold function, and the threshold function is still not differentiable. But we don't worry about that because we compute the gradients before that. So in that way, it's not a hindrance, and it will become more clear when I show you the code example. So here's just conceptually how it looks like when we fit an ADALINE model. And here what I'm doing is I'm showing you the class label on y-axis. So for binary classification, where we have two class labels of ones and zeros, I have plotted them here. So the class labels can be either 0 or 1, and then we have only one feature value for simplicity, and we want to predict that in the linear neuron it is a linear model. So essentially it will fit a linear line similar to the linear regression, except now the difference is that in linear regression we usually have continuous values, not only zeros and ones, and we don't have threshold function. So in the ADALINE, after fitting this model, we apply this threshold function, let's say at zero point 0.5 between 0 and 1. And we say then if something is bigger than a certain value, let's say prediction, if the prediction is greater than 0.5, produce class label 1, and otherwise produce class label 0. So in that way, we turn the continuous prediction into a class label. Again, this will become clear when I show you the code example. So let's just quickly go over coding this ADALINE model. Now note that this model is implemented using stochastic gradient descent. We could also implement it with gradient descent. It doesn't really matter, but here we use stochastic gradient descent, like the mini batch mode, because this is something we will also be doing later on when we implement deep neural networks. Now let me write the code and then we shall talk. Now again, these steps are all the same like we did in the previous video for linear regression, just using a different data set now. Now we are using the iris dataset where we have four features: x1, x2, x3, and x4. So that's sepal length, sepal width, petal length, and petal width. And this is our class label, the predicted class label. So I have actually simplified it. Now there are only two class labels. Now let me see. So I'm only using data points 50 to 150 here. So here I'm applying class label 1. So what I'm doing precisely is I'm selecting only data points 50 to 150, and these would be class labels 1 and 2, but I change them to 0 or and 1. Otherwise our function will not work. This is just to make this problem work for ADALINE. And also the same would be true for perceptron. Later on we will be seeing models that can also deal with multiple class labels. But for now we have only two class label models. Now let's write some more code. So here, this is exactly the same code as before, where I'm just using shuffle indices, now use for 70% again for training and 30% for testing. And also I'm standardizing the features and plot it just to visualize how the data looks like. So this is our data set, two classes, blue dots and the orange dots here. And this is for the training set, how the training set looks like. And below is the test set here, and we shall implement our ADALINE model now. Note that this is exactly the same as before, so I don't have to go over this again. So this is exactly like the code as in case of linear regression. This is basically what we do in backward pass, where we compute the derivative. So this is our outer derivative and these are the inner derivatives, and then we define the training and evaluation functions. This is somewhat similar to what we did before as well. Now compute the lost, we have our training function. Now one difference is now we are using mini batch gradient instead of batch gradient. We iterate over the epochs inside, we also iterate over the mini badges. So I'm creating a mini badge here and I'm creating multiple mini badges here by splitting this into mini badges of a certain size. So I'm using a size 10. So I'm splitting it into multiple vectors where each vector will contain 10 training examples, and then for each mini batch I'm doing my forward pass and so forth. And now I have the mini batch training, so that I have like if I have 150, I have 7 mini badges in each iteration because I have 700 training examples. So I can divide them into 10 mini badges with 70 training examples each. Now let's see how our model trains. Mm, So now we start with very large loss again. Um, like we start with a large mean square error. Then you can see it goes down, but it is now a little bit noisier. You can see it goes down here and then goes a little bit up, and you can see then it's a little bit noisy at these updates. And then overall per epoch, we can see that the things go down. So at some point we have converged. So we see that it's fluctuating a little bit, but it's now getting down significantly. It's going a little bit up and down, so it's a bit noisier than the gradient descent. The mini batch gradient descent is usually a bit noisier. Now time to evaluate it. Let me write some code again. So it's easier actually to look at it in a plot compared to these lists. This is something, if you train complicated neural network models, it might be helpful to print it on a command line on server if you don't have any plotting function available. But after training, it's usually good to at least look at it like this, because here it's a little bit more clearer to see. So you can see it goes down very steeply, and then you can see it fluctuates. So it's not converging completely because it's more stochastic, so there is more noise, but overall we can say that it kind of converges. Maybe we could have changed the learning rate, making the learning rate a little bit smaller, and later on we will also learn about something called learning rate schedulers, which we make the learning rates smaller over time so that we converge better also. Now let's just take a look at model weights and bias from the training and then compare to our analytical solution again. So we can see here that weights are 0.07 and 0.4 here, and 0.488. And if we look at our analytical solution, it's close. You can see it's quite close, but it's not as close as before, as we did with gradient descent instead of stochastic gradient descent. So before it was a little bit more accurate. So what you can do is change this code also to do gradient descent. Later on, when we talk about multi-layer networks, regular gradient descent wouldn't really be useful. So it's actually good to use stochastic gradient descent here as a practical already. All right, so let's take a look at the prediction accuracy now. Now, how good is our classifier that we trained? So for this one, we now need the threshold function. So we set the threshold at 0.5. So for a given value, if the value exceeds 0.5, the prediction exceeds 0.5, we assign it class value, class label 1. If it's below 0.5, we assign it class label 0. So this is what I'm implementing here. And now I'm also then computing the mean. So here first I'm creating these predicted labels, and then I'm checking how many of the predicted labels match my true labels. So this will be a vector of zeros and ones, and then I sum up all the ones and divide up the number of data points. So this is what the mean is doing. It's basically telling me on average how many times I am correct. So it will be a value between 0 and 1, and I do the same thing here for the test set also. So we get 90% training accuracy and 96% or text and 96% test accuracy. It's a small data set. Usually you will find that in real world case the test accuracy is usually lower than the training set accuracy, but because of this overfitting and stuff like that. But this is a very small data set, and this might be just due to chance. All right, so let's take a look at the decision boundary. So this is going to be the same code as from the perceptron, and we can see now on the left hand side this is for the training set, and on the right hand side it's for the test set. It's actually doing better than the perceptron, as if you remember, it's something, this would be a problem where the perceptron wouldn't be able to solve it, because here you can now see that this is a case where the classes are not linearly separable. So there is no decision boundary where you get perfect accuracy. So perceptron here would have really problems. It would change. It would like have a decision model that would flick back and forth, but this model converges. You saw that based on the training error. So it's kind of finding a good boundary here. And this is for the test set. So hope this was helpful. If you have any questions, drop a comment below. Make sure to like and subscribe. See you next time.